Hello. In this session, we will discuss about bonding in metals. Almost all of the transition metals form compounds in which carbon monoxide acts as a ligand. There are 3 points of interest with respect to these compounds. First point is that carbon monoxide is not ordinarily considered as a very strong Lewis base, and yet it forms strong bonds to the metals in these compounds. Second point of interest is that metals are always in a low oxidation state, formally in an oxidation state of 0, but sometimes also in low positive or negative oxidation states. And the third point of interest is that the 18 electron rule is obeyed by these complexes. And there are some exceptions. Example, vanadium that is VCO6 times, which contains 17 electron rule. But this molecule is paramagnetic in nature, containing 17 electron. It does not dimerize, and vanadium, this VCO6 is less stable than carbonyl complexes obeying 18 electron rules. It decomposes at 70 degrees Celsius and if given opportunities readily accepts an electron to form the 18 electron anion. This VCO6 times preferred to exist as an anion, that is VOC6CO6 minus. And in metal carbonates, carbon monoxide acts both as terminal and bridging ligand. See, for example, in this case CrCO6 times, this carbon monoxide unit exists as terminal ligands. This is another example. This is an example of polynuclear carbonates in which two metal atoms are present. Here also this carbonyl group exists as the terminal ligand. Whereas in the case of Fe2CO9 times, here you can see, in addition to this terminal ligand, this carbon monoxide acts as terminal position, occupies this terminal position. It also occupies the bridge. It also acts as bridging ligand. Okay. Now let's see the bonding in carbonyls in which carbon monoxide acts as terminal ligands. We know that carbon monoxide contains 14 electrons, and the electronic configuration of this carbon monoxide according to this molecular orbital concept, we can write it as sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2. Both of them have the same energy. This 2p, pi 2px and pi 2py, both of them have the same energy. And then comes sigma 2pz, and these are the anti-bonding molecular orbitals, that is pi star 2px0 and pi star 2py and sigma star 2pz. These are anti-bonding molecular orbitals, and these are LUMOs, that is lowest unoccupied molecular orbitals. These pi 2px, pi 2py and sigma 2pz belongs to highest occupied molecular orbitals, that are HOMOs. Okay, now here you can see that the pi star 2px and the pi star 2py molecular orbitals are the anti-bonding molecular orbitals, and there is no electrons in that. And we know that in metals or in metal ions there is number of vacant d orbitals. So we have found that in metal carbonyls have both sigma and pi bond character. This metacarbonyl, the bonding in metacarbonyl exhibits both sigma and pi character. To begin with, let's see. First, overlap takes place between the filled bonding 2p pi 2px and pi 2py molecular orbitals of carbonyl carbon with the empty d orbital of metal, resulting in the formation of a sigma bond. See this example. This figure represents the metal orbitals. These are filled d orbitals, which is represented by the pink color. These are filled d orbitals of metal ions, and the colorless orbital represents the vacant d orbital or empty d orbital of the metal ion. And this is the carbon monoxide, molecular orbitals of carbon monoxide, and here this black color filled orbital represents the pi 2p, that is the filled bonding pi 2px and pi 2py molecular orbitals of carbonyl atom, carbonyl carbon, and when it approaches each other, filled bonding pi 2px and pi 2py molecular orbitals of carbonyl carbonyl group overlap with the empty d orbital of the metal, okay, and resulting in the formation of a sigma bond. This is a vacant d orbital and this is a pi bonding molecular orbital, and results in the formation of a sigma bond. Okay, and these pi 2p orbitals represent the highest occupied molecular orbital which have the sigma symmetry, and since carbonyl group then since the carbonyl group is a or carbon monoxide is a weak Lewis base, the sigma bond thus formed between the central metal atom and the carbon atom is generally weak, is a weak bond. But we can see that from the experimental analysis it is found that the bonding between the metal and the carbonyl group is very strong. Okay. Now what in the second, there is another type of bonding observed in this metal carbonyls. The second type of bond formed is because of the overlap between the filled metal d orbitals with the empty anti-bonding pi 2p molecular orbitals of carbon monoxide, resulting in an additional pi bond between the metal and the carbon monoxide. Both of them have pi symmetry and pi symmetry, and antibonding 2p molecular orbital of carbon monoxide is LUMO, that is lowest unoccupied molecular orbitals. Okay, now this is the interaction, this is the overlap, and resulting in the formation of pi bonding. Okay, and the pi bonding interaction leads to the delocalization of electrons from the filled d orbitals onto the carbon monoxide ligand. So the ligand also acts as a pi acid ligand. Okay, and what are pi acid ligands? Carbon monoxide acts as a pi acid. What are pi acid ligands? The ligands capable of accepting appreciable amount of pi electron density from the metal atoms to the empty pi or pi star orbitals of their own are called pi acid ligands. And the ability of carbon monoxide to delocalize electron density from metal accounts for the prevalence of d metal carbonyls with a zero or negative oxidation state. Now let's see bonding in carbonyls in which carbon monoxide acts as bridging ligand. A large number of polynuclear carbonyl species contains bridging carbonyl groups, bridging carbonyl ligands in addition to the terminal carbonyl ligands. See, this is an example. Here there are three carbonyl groups which are acting as bridging ligands. A bridging carbonyl ligand is always accompanied by a metal-metal bond which leads to the extensive delocalization in the metal-carbon-metal moiety involving overlap of metal orbitals with both sigma and pi molecular orbitals of carbon monoxide. See these examples. Here this this is the sigma bonding molecular orbital of this carbon monoxide. This overlap with the d orbitals of metal atom, and similarly in this case these are the pi molecular orbitals of carbonyl groups, and this is overlap with the orbitals of metal, d orbitals of metal atom. Overlap of sigma and pi orbitals of bridging carbonyl ligands with the d orbitals of metal atoms. The sigma orbital of carbon monoxide can donate electron density to the metal orbitals, and empty pi star orbital of carbon monoxide can accept electrons from the d orbitals. Now let me conclude this session. In this part we discussed about the bonding in metal carbonyls in which carbon monoxide acts both as a bridging ligand as well as a terminal ligand. Thank you.